S be the element of a surface, and let epsilon be the angle which a normal to the surface drawn towards the positive side of the surface makes with the direction of the vector quantity r. Then the integral over the surface of r times cosine epsilon ds is called the surface integral of r over the surface S. Theorem 3. The surface integral of the flux through a closed surface may be expressed as the volume integral of its convergence taken within the surface. See Article 25. Let xyz be the components of r, and let L, L, M, N be the direction cosines of the normal to S measured outwards. Then the surface integral of r over S is Wolff-Temperes. The integral over the surface of r cosine epsilon ds equals the integral of xl ds plus the integral of ym ds plus the integral of zn ds, which is the same as the integral of x dy dz plus the integral of y dz dx plus the integral of z dx dy. The values of x, y, z being those at a point in the surface, and the integrations being extended over the whole surface. If the surface is a closed one, then when y and z are given, the coordinate x must have an even number of values, since a line parallel to x must enter and leave the enclosed space an equal number of times, provided it meets the surface at all. Let a point traveling from x equals minus infinity to x equals plus infinity first enter the space when x equals x1, then leave it when x equals x2, and so on. And let the values of x at these points be x1, x2, and so on. Then the integral of x dy dz equals the integral of open square bracket x of 2 minus x of 1 plus x of 4 minus x of 3 plus and so on, close square bracket dy dz. Equation 2. If x is a quantity which is continuous and has no infinite values between x1 and x2, then x2 minus x1 is equal to the integral from x1 to x2 of dx by dx. Equation 3. Where the integration is extended from the first to the second intersection, that is, along the first segment of x, which is within the closed surface. Taking into account all the segments which lie within the closed surface, we find theta wide. The integral of x dy dz is equal to the triple integral of dx by dx, dx dy dz. Equation 4. The double integration being confined to the closed surface, but the triple integration being extended to the whole enclosed space. Hence, if x, y, z are continuous and finite within a closed surface S, the total surface integral of r over that surface will be the surface. The surface integral of r cosine epsilon ds equals the triple integral of dx by dx plus dy by dy plus dz by dz, all multiplied by dx dy dz. Equation 5. The triple integration being extended over the whole space within S. Let us next suppose that x, y, z are not continuous within the closed surface, but that at a certain surface capital sigma y of x, y, z equals 0, the values of x, y, z alter abruptly from x, y, z on the negative side of the surface to x prime, y prime, z prime on the positive side. If this discontinuity occurs, say between x1 and x2, the value of x2 minus x1 will be equal to the integral from x1 to x2 of dx by dx plus x prime minus x, all multiplied by dx. Equation 6, where in the expression under the integral sign only the finite values of the discontinuity are to be considered. The whole expression for the total surface integral of r over the closed surface will be expressed by the integral of r cosine epsilon ds equals the triple integral of dx by dx plus dy by dy plus dz by dz dx dy dz plus the integral of x prime minus x dy dz plus y prime minus y dz dx plus z prime minus z dx dy. Equation 7. Or if L prime, M prime, N prime are the direction cosines of the normal to the surface of discontinuity, and ds prime an element of that surface, the integral of r cosine epsilon ds equals the triple integral of dx by dx plus dy by dy plus dz by dz dx dy dz plus the integral of L prime times x prime minus x plus M prime times y prime minus y plus N prime times z prime minus z ds prime. Equation 8, where the integration of the last term is to be extended over the surface of discontinuity. If at every point where x, y, z are continuous, dx by dx plus dy by dy plus dz by dz equals 0. Equation 9, and at every surface where they are discontinuous, L prime x prime plus M prime y prime plus N prime z prime equals L prime x plus M prime y plus N prime z. Equation 10. Then the surface integral over every closed surface is 0, and the distribution of the vector quantity is said to be solenoidal. We shall refer to equation 9 as the general solenoidal condition, and to equation 10 as the superficial solenoidal condition. Now let's consider the case in which at every point within the surface S, the equation dx by dx plus dy by dy plus dz by dz equals 0 is fulfilled. Equation 11. We have as a consequence of this the surface integral over the closed surface equal to 0. Now let the closed surface S consist of three parts, S1, S0, and S2. Let S1 be a surface of any form bounded by a closed line I1. Let S0 be formed by drawing lines from every point of I1 always coinciding with the direction of R. If L, M, N are the direction cosines of the normal at any point of the surface S0, we have R cosine epsilon equals XL plus YM plus Zn equals 0. Equation 12. Hence, this part of the surface contributes nothing towards the value of the surface integral. Let S2 be another surface of any form bounded by the closed curve I1 lying on the other side of the surface S0. Let Q1, Q0, Q2 be the surface integrals of the surfaces S1, S0, S2, and let Q be the surface integral of the closed surface S. Then Q equals Q1 plus Q0 plus Q0 plus Q2 equals 0. Equation 13. And we know that Q0 equals 0. Equation 14. Therefore, Q equals minus Q1. Equation 15, or in other words, the surface integral over the surface S2 is equal and opposite to that over S1, whatever be the form and position of S2, provided that the intermediate surface S0 is one for which R is always tangential. If we suppose I1 a closed curve of small area, S0 will be a tubular surface having the property that the surface integral over every complete section of the tube is the same. Since the whole space can be divided into tubes of this kind, provided dx by dx plus dy by dy plus dz by dz equals 0. Equation 16. A distribution of a vector quantity consistent with this equation is called a solenoidal distribution. Tubes and lines of flow. If the space is so divided into tubes that the surface integral for every tube is unity, the tubes are called unit tubes. And the surface integral over any finite surface S bounded by a closed curve L is equal to the number of such tubes which pass through S in the positive direction, or, what is the same thing, the number which pass through the closed curve L. Hence, the surface integral of S depends only on the form of its boundary L and not on the form of the surface within its boundary. On peripheretic regions, if throughout the whole region bounded externally by the single closed surface S1, the solenoidal condition dx by dx plus dy by dy plus dz by dz equals 0 is fulfilled, then the surface integral taken over any closed surface drawn within this region will be 0. And the surface integral taken over a bounded surface within the region will depend only on the form of the closed curve which forms its boundary. It is not, however, generally true that the same results follow if the region within which the solenoidal condition is fulfilled is bounded otherwise than by a single surface. For if it is bounded by more than one continuous surface, one of these is the external surface and the others are internal surfaces. And the region S is a peripheretic region, having within it other regions which it completely encloses. If within any of these enclosed regions, call one S1, the solenoidal condition is not fulfilled, let Q1 equal the surface integral of R cosine epsilon ds. This is the surface integral for the surface enclosing this region, and let Q, Q3, and so on be the corresponding quantities for the other enclosed regions. Then, if a closed surface S' is drawn within the region S, the value of its surface integral will be 0 only when this surface S' does not include any of the enclosed regions S1, S2, and so on. If it includes any of these, the surface integral is the sum of the surface integrals of the different enclosed regions which lie within it. For the same reason, the surface integral taken over a surface bounded by a closed curve is the same for such surfaces only bounded by the closed curve as are reconcilable with the given surface by continuous motion of the surface within the region S. When we have to deal with a peripheretic region, the first thing to be done is to reduce it to an aperiphratic region by drawing lines joining the different bounding surfaces. Each of these lines, provided it joins surfaces which were not already in continuous connection, reduces the periphratic number by unity, so that the whole number of lines to be drawn to remove the periphraccy is equal to the periphratic number, or the number of internal surfaces. When these lines have been drawn, we may assert that if the solenoidal condition is fulfilled in the region S, any closed surface drawn entirely within S and not cutting any of the lines has its surface integral 0. In drawing these lines, we must remember that any line joining surfaces which are already connected does not diminish the periphery, but introduces cycles. The most familiar example of a peripheretic region within which the solenoidal condition is fulfilled is the region surrounding a mass attracting or repelling inversely as the square of the distance. In this case, we have x equals mx over r cubed, y equals my over r cubed, z equals mz over r cubed, where m is the mass supposed to be at the origin of coordinates. At any point where r is finite, dx by dx plus dy by dy plus dz by dz equals 0. But at the origin, these quantities become infinite. For any closed surface not including the origin, the surface integral is 0. If a closed surface includes the origin, its surface integral is 4 pi m. If for any reason we wish to treat the region round M as if it were not peripheretic, we must draw a line from M to an infinite distance. And in taking surface integrals, we must remember to add 4 pi m whenever this line crosses from the negative to the positive side of the surface, on right-handed and left-handed relations in space. In this treatise, the motions of translation along any axis and of rotation about that axis will be assumed to be of the same sign when their directions correspond to those of the translation and rotation of an ordinary or right-handed screw. For instance, if the actual rotation of the Earth from west to east is taken positive, the direction of the Earth's axis from south to north will be taken positive. And if a man walks forward in the positive direction, the positive rotation is in the order hand right, the order head left. If we place ourselves on the positive side of a surface, the positive direction along its bounding curve will be opposite to the motion of the hands of a watch with its face towards us. This is the right-handed system, which is adopted in Thomson and Tate's Natural Philosophy, section 243. The opposite or left-handed system is adopted in Hamilton's and Tate's Quaternions. The operation of passing from one system to the other is called, by listing, perversion. The reflection of an object in a mirror is a perverted image of the object. When we use the Cartesian axes x, y, z, we shall draw them so that the ordinary conventions about the cyclic order of the symbols lead to a right-handed system of directions in space. Thus, if x is drawn eastward and y northward, z must be drawn upward. The areas of surfaces will be taken positive when the order of integration coincides with the cyclic order of the symbols. Thus, the area of a closed curve in the plane of xy may be written either the integral of dx dy or minus the integral of y dx, the order of integration being xy in the first expression and yx in the second. This relation between the two products dx dy and dy dx may be compared with that between the products of two perpendicular vectors in the doctrine of quaternions, the sign of which depends on the order of multiplication, and with the reversal of the sign of a determinant when the adjoining rows or columns are exchanged. For similar reasons, a volume integral is to be taken positive when the order of integration is in the cyclic order of the variables x, y, z, and negative when the cyclic order is reversed. We now proceed to prove a theorem which is useful as establishing a connection between the surface integral taken over a finite surface and a line integral taken round its boundary. Theorem 4. A line integral taken round a closed curve may be expressed in terms of a surface integral taken over a surface bounded by the curve. Let x, y, z be the components of a vector quantity q, whose line integral is to be taken round a closed curve A. Let S be any continuous finite surface bounded entirely by the closed curve A, and let xi, eta, zeta be the components of another vector quantity S related to x, y, z by the equations xi equals dz by dy minus dy by dz, eta equals dx by dz minus dz by dx, zeta equals dy by dx minus dx by dy. Equation 1. It is manifest that xi, eta, zeta fulfill of themselves the solenoidal condition dxi by dx plus d eta by dy plus d zeta by dz equals 0. Let Lmn be the direction cosines of the normal to an element of the surface ds reckoned in the positive direction. Then the value of the surface integral of S may be written the integral over the surface of open bracket Lxi plus m eta plus n zeta close bracket ds. Equation 2. In order to form a definite idea of the meaning of the element ds, we shall suppose that the values of the coordinates x, y, z for every point of the surface are given as functions of two independent variables alpha and beta. If beta is constant and alpha varies, the point xyz will describe a curve on the surface. And if a series of values is given to beta, a series of such curves will be traced, all lying on the surface S. In the same way, by giving a series of constant values to alpha, a second series of curves may be traced, cutting the first series and dividing the whole surface into elementary portions, any one of which may be taken as the element ds. The projection of this element on the plane of yz is, by the ordinary formula, LDS equals dy by d alpha dz by d beta minus dy by d beta dz by d alpha d beta. Equation 3. The expressions for MDS and NDS are obtained from this by substituting zxy and xyz in cyclic order. The surface integral which we have to find is the integral of open bracket L psi plus m eta plus n zeta close bracket ds. Equation 4, or substituting the values of psi, eta, zeta in terms of xyz, the surface integral is the integral over S of open bracket m times dx by dy minus dy by dx plus n times dy by dz minus dz by dy plus L times dz by dx minus dx by dz close bracket ds. Equation 5, the part of this which depends on x may be written as the double integral of open bracket m dx by dy minus L dx by dz close bracket ds. That is equal to the double integral of dx by d alpha dx by d beta minus dx by d beta dx by d alpha d beta. Equation 6. Adding and subtracting dx by dx d alpha d beta, this becomes the double integral of d by d alpha of x dx by d beta minus d by d beta of x dx by d alpha d beta. Equation 7. As we have made no assumption as to the form of the functions of alpha and beta, we may suppose that a is a function of x, or in other words, that the curves for which alpha is a constant are those for which x is constant. In this case, dx by d beta equals 0, and the expression becomes by integration with respect to alpha, the integral of dx d beta d alpha equals the integral of x dx d beta. Equation 9, where the integration is now to be performed round the closed curve. Since all the quantities are now expressed in terms of one variable beta, we may make beta the length of the bounding curve, the independent variable, and the expression may then be written as the integral of x dx by ds. Equation 10, where the integration is to be performed round the curve A. We may treat in the same way the parts of the surface integral which depend upon y and z, so that we get finally the surface integral of open bracket Lxi plus m eta plus n zeta close bracket ds equals the line integral of x dx by ds plus y dy by ds plus z dz by ds all multiplied by ds. Equation 11, where the first integral is extended over the surface S and the second round the bounding curve A, on the effect of the operator del on a vector function. We have seen that the operation denoted by del is that by which a vector quantity is deduced from its potential. The same operation, however, when applied to a vector function, produces results which enter into the two theorems we have just proved, Theorem 3 and Theorem 4. The extension of this operator to vector displacements and most of its further development is due to Professor Tate. Let sigma be a vector function of rho, the vector of a variable point. Let's suppose, as usual, that rho equals ix plus jy plus kz and sigma equals ix plus jy plus kz, where x, y, z are the components of sigma in the directions of the axes. We have to perform del on sigma, or the operation del dot sigma equals dx by dx plus dy by dy plus dz by dz, and del cross sigma equals I times open bracket dz by dy minus dy by dz close bracket plus j times open bracket d x by dz minus dz by dx close bracket plus k times open bracket dy by dx minus dx by dy close bracket. If the relation between x, y, z and xi, eta, zeta is that given by equation 1 of the last theorem, we may write del cross sigma equals I xi plus j eta plus k zeta. See Theorem 4. It appears therefore that the functions of x, y, z which occur in the two theorems are both obtained by the operation del on the vector whose components are x, y, z. The theorems themselves may be written the triple integral of del dot sigma ds equals the surface integral of sigma dot u v ds, Theorem 3, and the line integral of sigma dot d rho equals the surface integral of s dot u v ds, Theorem 4, where ds is an element of a volume, ds of a surface, d rho of a curve, and uv a unit vector in the direction of the normal. To understand the meaning of these functions of a vector, Let us suppose that sigma naught is the value of sigma at a point P, and let us examine the value of sigma minus sigma naught in the neighborhood of P. If we draw a closed surface around P, then if the surface integral of sigma over this surface is directed inwards, del dot sigma will be positive, and the vector sigma minus sigma naught near the point P will be on the whole directed towards P, as in the figure 1. I propose therefore to call the scalar part of del sigma the convergence of sigma at the point P. To interpret the vector part of del sigma, let us suppose ourselves to be looking in the direction of the vector whose components are xi, eta, zeta, and let us examine the vector sigma minus sigma naught near the point P. It will appear as in the figure 2, this vector being arranged on the whole tangentially in the direction opposite to the hands of a watch. I propose therefore, with a view to distinctness, to call the vector part of del sigma the curl, or the version of sigma at the point P. At figure 3, we have an illustration of curl combined with convergence. Let us now consider the meaning of the equation del dot sigma equals 0. This implies that del dot sigma is a scalar, or that the vector sigma is the slope of some scalar function psi. These applications of the operator del are due to Professor Tate. A more complete development of the theory is given in his paper on Green's and other allied theorems, to which I refer the reader for the purely quaternion investigation of the properties of the operator del. One of the most remarkable properties of the operator del is that when repeated it becomes del squared equals minus the quantity open bracket d squared by dx squared plus d squared by dy squared plus d squared by dz squared close bracket. This is an operator occurring in all parts of physics, which we may refer to as Laplace's operator. This operator is itself essentially scalar. When it acts on a scalar function, the result is scalar. When it acts on a vector function, the result is a vector. If with any point P as center, we draw a small sphere whose radius is r, then if q naught is the value of q at the center, and q bar the mean value of q for all points within the sphere, q naught minus q bar equals minus 1/6 r squared del squared q. Equation 2. So that the value at the center exceeds or falls short of the mean value according as del squared q is positive or negative. I propose therefore to call del squared q the concentration of q at the point P, because it indicates the excess of the value of q at that point over its mean value in the neighborhood of the point. If q is a scalar function, the method of finding its mean value is well known. If it is a vector function, we must find its mean value by the rules for integrating vector functions. The result is, of course, a vector.